so on, although I have dealt with Norwegian colleagues, so something of the Norwegian gas-led system. Talk a bit about upstream. And we've got the national transmission system, which is the main high pressure system in the UK, and then what in this country are known as the distribution networks. Although they're called distribution, they still have quite a wide range of pressure regimes. So in the UK, this is UK continental shelf offshore infrastructure. You can get this sort of information on a government website, but you can see that there's, I remember to bring the pointer this time. You've got a whole number of fields up here in the northern North Sea. Generally those fields are what's called associated gas, so they're both gas and oil production. In some ways, the oil has always been more important than the gas, so the gas has flowed whatever because the oil's the thing with the value. Whereas down here in the southern North Sea, it's what's called dry gas. So essentially it's gas production and has become more commercial in terms of its production. But you've got a whole range of subsea pipelines here, but you can see they come in and hit the UK, up there St Fergus, Teesside, Easington, Bacton on the coast there, and there's a little bit coming into northwest of England. So where, I suppose, my previous experience lies is once it reaches the beach. So at one time, all the gas, the UK was pretty much self-sufficient in terms of gas supply. All the gas came from those North Sea fields we call them beach terminals. Number of pipelines coming in, but there are now also interconnectors, so they're bi-directional pipelines. In particular, there's one between here and Belgium, and it can flow either way, and it's not based on physical reasons what they choose to do on any given day. It's commercial pricing. What's the price of gas today on the market in the UK versus a continental hub? There's also an interconnector between here and Ireland, but physically it can't reverse flow because Ireland doesn't have enough gas, but they have recently commissioned new terminals and new gas fields in Ireland. Newer into the pot are regasification terminals, importation terminals. Isle of Grain down in Kent, and two at Milford Haven, and gas has come from all over the world. There was suggestions that we might start to receive lots of shale gas from the US. In fact, some of the most recent gas has come from Peru. So it's a very global picture. But the gas is coming to Qatar is the predominant source, but also Algeria, Nigeria, Trinidad and Tobago, Norway. I think we've maybe had one come as far as Australia. Indonesia, I think, tends not to, because that will tend to get attracted to South Korea and Japan. There's almost like a Pacific hub, and Middle East sits in between. So. And we've seen very little LNG into the UK this winter because it's all been going to South Korea and Japan. Hence strange things like Peruvian gas, partly because I think they've widened the Panama Canal, and it can take very big boats now. So, but then US gas can go round to the west. So historically, when I started in the UK gas industry, it was the gas landed, British Gas controlled everything. They said what happened. Completely different picture now. I think at the beginning of the course you get a talk on sort of almost like some of these market commercial aspects of gas. Sure. Yeah. So then we've got the national transmission system, which is a high pressure system, sort of components. We've got compression, which I suspect has been rather heavily used this winter because there's been a lot more gas coming back into Scotland. A lot of pipelines, MOP ratings anywhere up to 94 bar, but historically it was 70 bar, but it's crept, so you've got 75 bar, 84 bar, 85 bar, 94 bar. Block valves so they can isolate. Control valve sites so you can actually manage and control flow. And offtakes where the various next stage consumption of gas takes place. And then we've got storage, So there's one large offshore storage, an offshore field, depleted field, Rough. However, that's been having a lot of integrity issues, and they have asked to go to zero usable capacity because they have certain requirements to store gas, but I think due to well integrity issues, due to ageing, which you've probably heard plenty about in previous weeks, Rough is a good case example of an ageing asset that is now struggling to maintain pressure. And the amount they can store is fundamentally dependent on the well pressures. Back in my very early days, about 30 years ago, I was involved in commissioning Rough. And then we've got the regional distribution systems, and I've got a slide that will illustrate a little bit more about that coming up in a little bit. So UK gas supplies, so this is how it looked in winter 2013-14. So we have a chunk of gas coming in St Fergus, and a lot of that is Norwegian gas, it's not UK gas. So it can come to this country, or it can go to Germany or Belgium or France. Teesside used to be big, is sort of diminished somewhat. Easington, big Norwegian pipeline, Langeled, which I think was, maybe still is, the world's longest subsea pipeline. If you go from the Ormond Lang field to Easington, I think it's about 1,100 kilometres. Well, it goes through, it's in two sections, Sleipner.
Goes through the Humber gas plant?
Yeah. So for my sins, I got to know a bit about Norway, and I've been over to. Are you Gasco or Statoil?
I was working up in Germany.
Right, okay, yeah. So yeah, we'd be watching what's happening at Dornamend, and particularly 2 or 3 years ago, if they had problems, you get trips and you get them big losses of supply, and you're trying to see where the gas is going.
Excuse me. Is it cheaper for you to use Russian gas or shale gas from USA?
At the moment, well, strictly speaking, I don't think we get a single molecule of Russian gas. It doesn't reach the UK. However, because it comes into Germany, that means Norwegian gas and Dutch gas that comes into that can then go through the BBL pipeline into Netherlands. So in a sense, it's all a bit like pushing the tiles around and finding where the space is. But it's all about it is about the economics. And LNG economics is a bit of a weird and wonderful one. It seems to be feast or famine. There's either too much supply and not enough demand, or vice versa. No, sometimes boats are looking for places. So we've had years where LNG has come in, it's been very cheap. And then, say this winter, it's been very much pipeline gas. But we've seen less gas coming in from the Netherlands, and some of that is because some of their own production is limited. The Groningen field, which is the big historic field anyway, we don't directly get that gas in the UK because it's not suitable for UK consumption, but the Dutch government has restricted the amount of production a year because of earth tremors. But also shale unloading hasn't got going in a big scale yet. I think there's possibly two US terminals have got into this reloading thing. But again, it's the economics of how long it takes a boat, how long a boat costs. And now if they can get through the Panama Canal and get to South Korea, Japan, where they're absolutely reliant on LNG. So when they had the Fukushima disaster some years ago, we knew that the gas would flip to South Korea, to Japan, because they had to have it. They closed down the nuclear generation for a period, so they had to source it another way, and world prices shifted, and we started seeing very little coming in. Then it shifted again, LNG became cheap, but it seems to vary on like a seasonal basis, and it depends which bit of the world's decided to have a cold winter this year. Last couple of winters have been very cold in the US and Canada. Been milder there this year. I think again it depends on as they get towards the end of the winter. We've started seeing cargoes coming in this month because I think the Far East winter is essentially over, so the concerns are less the. We might see Russian gas. There's talk of building a hop, effectively, but bypassing some of the European countries. But at the moment, while Britain is in the EU, there are rules around. Now, the EU is very keen to encourage interconnection, that capacity is offered in both directions commercially. So if you're German, you can't say this is German gas. You've got to release it to the market. Okay, emergency circumstances, there is EU legislation. I guess will be an interesting one to see how it develops over the next 2 years or so. It's one of the trade things to go on. Backturn has some UK gas coming in, but that's where the interconnection is with the continent. There's a Belgian pipeline, but they operate at up to 120 bar at a push. But what they choose to operate it is a matter of economics as well as pressure integrity. That they're your 2 LNG terminals, and you can see that although they're actually quite big beasts, they could supply probably, if they were all outputting at the same time, probably half of the UK supply today. You can see that actually the percentage they did supply are quite modest, because the economics didn't say LNG should flow in that particular year. Seasonal storage. So this comment may be coming rapidly out of date. This winter, rough in principle, has about 3,500 million cubic metres. What's that, about 39 terawatt hours, if you like to think in energy terms. But this winter it's been curtailed due to integrity issues, and there's no guarantee they're going to be able to resolve those over the summer. So that's a depleted gas field. Then we've got salt cavities, if the geology is right, and they're typically sized between 40 and 300 million cubic metres. And just to give you a sort of scale, UK demand on a coolish winter's day will be about 300 million cubic metres at the moment. Again, the economics are favoured using gas-fired power stations rather than coal-fired, and it depends if it's a windy day or not. That can swing demand a lot now. It does interact with wind generation. There's some depleted onshore fields. There's in the south of England, Humbley Grove. That's an old oil gas field, so they pump it in. But I put seasonal in inverted commas in that the old model tended to be fill all summer, empty all winter. However, a lot, particularly these latter types, the salt cavities and depleted onshore fields, are intended to be fast cycle, so they can actually be fill at the weekend, empty during the week, because there's less demand naturally at the weekend. Gas price falls, inject it cheap, make a couple of pence a kilowatt hour on it by withdrawing it the next week, so, and you can get them flip-flopping. The operators don't like the commercial staff who tell them, midnight, turn it around please. Do the opposite of what you've been doing all day. But there are something of a commercial hedging tool, and so this is sort of an idea of what historically you got seasonal storage. So your available supplies went up and down through the year, but we have like a summer dip here where temperature sensitive demand's gone off, nobody's got the heating on, even electricity demand has gone down. A lot of what you would read as demand is actually injection into storage or export to the continent. How does all this relate to yourselves as pipeline people? Well, probably through pressure systems as much as anything. So if we look at the offshore pipelines, I think some of the Asgard stuff, you might be able to correct me, operates up to 200 bar, sort of the northern Norwegian sector. So you've got some very high pressure stuff lurking around there. National transmission system, 31 bar would be about the lowest pressure that you'd see on the very furthest extremity at the, depending on the swing on the system and depending on the demand on the day. And 94 bar is the maximum operating pressure anywhere on the system. And then there are a range of different MOP ratings. So what you've got is a set of pressure systems. And then if we go into the salt cavities, there's two types. Essentially, there's in Cheshire, it's quite shallow. They operate at low pressure, so they have to compress out to lift the pressure and free flow in if they can. Over on the East Yorkshire coast, Hornsey and Aldborough operate up to 140 bar because they're about 3,000 metres deep, and therefore they have to compress in because there isn't the pressure in the transmission system to free flow it in. But then we have to be protected from their pressures when they export. So if there's any fault on their equipment, the 70 bar system is not exposed to 140 bar pressures. And then once you get into the regional distribution systems, you've got anything from, they do have some higher 70 bar pipelines down to 14 bar, what they'll call intermediate pressure, 7 bar, so that typically come towards like a city edge. Medium pressure, sort of your bulk local distribution, but you will get that in populated areas, and eventually the low pressure mains somewhere 50 millibar and below. So you've got a good old range of pressure regimes there, and a lot of the pressure control devices we'll talk about are about protecting downstream systems from upstream systems. A little bit about sort of pressure lossing systems. It's sort of a bit like a square law type of thing. So starts off at 70 bar, you would start to lose your pressure as you go down for a typical pipe. So what we do, we stick compression on at this point, and compressors themselves will then have to have control systems attached to them. So typically this is Scotland. So this winter there's been best part of 100 million cubic metres a day coming through St Fergus through the 3 terminals. So there's compression here at Aberdeen, here at Kirriemuir.
So it's every 80 kilometres
there? It's typical, yeah. One time it used to be about every 40 miles, but then as they've uprated things. Well, the other thing now is people want to be able to flow flexibly. So old-fashioned capacity rules said, right, 80 metres a day, work out the size of your pipe, what's your pressure loss, where does your next compressor lie. However, the system swings a lot more now, and I'll say a bit more why that might be the case. So you get much more pressure swing, but also produces profile, either for physical reasons. So if you're offshore and you've only got a low flow, what they might do is try and run the compressors in 12 hours and then turn them off. So the interconnector quite often does that, it batches the flows up, because a compressor designed to flow 60 million a day doesn't like doing 5 million. It's better to flow for 4 hours at 6 times the rate. But then that means you're imposing profile on the next tier down the system. So you might have to use your compression to make space to absorb profiling. And then you get the awkward ones like where somebody's built a big power station on the end of a transmission line and you're trying to predict when they'll come on. So they're generally pumping that way, but again, flexible use of the system now says in some cases they want to be able to turn compressors around so they can pump in the opposite direction. So if gas comes into South Wales at Milford Haven, pump away from South Wales. If there's no gas coming in, pump into South Wales. So you've got to design your systems to accommodate. This is the northern LDZ, i.e. the one that covers Newcastle. So don't worry too much about the detail, but if you look, you can see there's a number of different colours on here. So there's the national transmission system coming through here. There's like a 38 bar spine that runs from somewhere north of Newcastle to round about Bishop Auckland, which is say halfway between Durham and Darlington. So then you've got this 19 bar system which goes all the way across the Pennines and has an offtake here. So the gas is flow controlled from the national system into these regional systems, and then you've got like this sort of 7 bar system that will operate close to the city. So there's a whole range of pressure tiers, and as you can see, they just reflect the number of different systems, and some of this is now for historical reasons. Now, if you were designing the system from scratch, you probably wouldn't end up with this, but it's evolved over goodness knows how many years. And then you've got you and I, the customer, who are awkward. We don't take our gas nice and flat. We follow this diurnal profile. So heating comes on in the morning, heating comes on at tea time. So there's a period in the day when instantaneous demand would exceed flat supply. Historically, gas was taken into the distribution systems at a flat rate, and the idea was the national transmission system operated at a nice flat 1/24th rate. Not any longer. And power stations, they like to generate, a lot of them 2 shifts, so they'll come on in the morning and they'll operate till 9 o'clock, 10 o'clock, and then they switch off overnight. It means they take their gas like that. So again, they're imposing swings. So pressure swing, and therefore I suppose pressure cycling and stressing of the national system has changed radically in recent years. Diurnal storage, decliningly available in the regional systems. Line pack, basically if you put less gas in than you're taking out, your pressure will fall, and what you're doing is you're taking the stored volume out of the pipeline, and that stored volume that's inherently in the pipeline is what we call line pack. And all systems deal with, you look at interconnector, they'll tell you how much stock they've got in. Gasco are monitoring their stock. It's a measure that gets published on an hourly basis for the national system, because in a way it's a measure of it's an illustration of the balance in the system. The regional systems, regional distribution systems, do have some line pack available. They can operate to a maximum and operate to a lower minimum, and therefore release the stored gas as demand varies. There's 1 or 2 bits of salt cavities that some regions have access to, but again that was unique to northern and northwest. Most regional transmission systems don't have access to it. High pressure storage vessels, above ground ones, not popular anymore. Most of them were historically built quite close to centres of population, and with all the risk that a high pressure vessel in a above ground high pressure vessel poses close to people, they've generally been closed down. And old fashioned low pressure gas holders, I think, have all bar gone now. So that there used to be a number along the Tyne, so they were associated with the old Towns gas production, and again you could fill them up overnight and empty them during the day, and this smoothed out demand. But they've gone, so the thing that's picked it up is the national transmission system. So pipeline control strategies, the majority are, and I use pipeline in its broadest sense, so all the way down to local distribution mains. I'm not just talking high pressure here, but the majority is under pressure control, and actually it's just continuous. So you have a set pressure that you desire to maintain at your source into the network, and it sits at that all the time. It's not managed, it's not varied over time. But what you also have are protective devices, because inevitably you've got one of these pressure boundaries. If your first controlling element fails, you need to protect the downstream element. You don't want a 38 bar regional system seeing 94 bar coming from the NTS. So there are safe protective pressure devices. Volumetric or flow control, if you want to manage the rate of transfer of flow from one system to another and let the pressure vary, you use volumetric control. but volumetric control often comes with pressure overrides, i.e. I'm quite happy to let the pressure vary, but it can't go above that and it can't go below that. So the pressure override will kick in and protect the downstream system for either seeing too much or equally too little, i.e. there's not enough pressure to keep pressure sufficient to maintain all the subsequent stages of supply. And boundary pressure control is where the actual point of control, let's say for example a compressor, the pressure boundary isn't there, it's somewhere downstream, so they'll telemeter back, they'll bring back measurements and control the compressor and limit it. So there are a number of those used on compressors, particularly for pipelines being uprated. So what was an all 70 bar at one time, if you uprate, let's say the first half of it to 75 bar, you want to get your 75 bar out of the compressor, but you don't want the downstream 70 bar bit to see pressure excursions. So a boundary pressure control is a form of protective system, but in principle it can be continuous. It usually has a number of elements, so I'll try and control first, and if I don't control well, then have a sort of a trip type mechanism. Oops, went up there. Right. So that's in a sense, the overview, and then we get into control and measurement systems. I think, what's that taking us? That's taking about half an hour. So if we look at about 45 minutes worth of this, and then we'll see if you've lost the will to live. So talk about components, some control basics.
I will examine that.
I refuse to answer that question on the grounds I might incriminate the course. Certainly, the idea of that first bit is to give context. So name all the pressure tiers that Northern LDZ has. Nope. Then some typical actual control valves and actuators. So this is a bit conceptual, theoretical, and could apply to all. It isn't just to gas pipelines, oil pipelines. It's also essentially control in its widest sense. But because this is only 3 hours, it took me a year to do a master's course in control. So we're not going to run through the whole gamut of frequency response and bode plots and all that sort of stuff. There simply isn't the time. So it's some basic practical control, and then say something about sensors and transducers, because to do some of this stuff you've got to make measurements. So control basics. So simple feedback control. The majority of control systems are based on feedback control, and how it works is, so you make a measurement within your process, and a lot of this will refer to process. So in this context, it's maybe pressure control. So your process is a pressure control system, but it could equally be a flow control system. It could be a temperature control system. Compare it with a measured value. So you've got a desired value, a set point. It might be that you say, I always want 1 bar going into that system. Or it might be that you want things to vary according to some sort of commercial schedule. Right, I'm going to produce 10 units of gas till that time, and then 8 units of gas, because that's what my customers' nominations say. But you compare the two, you've got an error. How far am I away from my target? Which goes into a control algorithm. And then you've got the controller, which drives the process via the final control element, a valve, a compressor. And you try and bring it towards set point, either in the face of set point changes or disturbances in the process. So in a pressure system, what happens if demand changes? Well, if you don't do anything, your pressure will either fall or rise, so you need to make some adjustments. So, little diagram that illustrates this. So we've got our set point, and we've got our measured value through some sort of sensor. The process might be a pipeline with some demand on it. Take a measurement, feed it back, plus minus, generates an error. A control algorithm, which we'll talk more about, drives the controller output. You might need some sort of interface, because this might be a computer, but actually some of the examples we'll show are actually very simple pneumatic. So
to transfer the signal, yeah?
yeah, so if I've got an electronic control, and there's an example later on, that will generate only an electronic output. I'm trying to move a valve somehow, so I've got to go through some sort of interface to translate.
How do we usually move the valves? Is it by electricity or?
The majority are to translate. You need some form of electro-pneumatic. So you'll find 4 to 20 milliamp signal is quite a common electric signal to go around sites and plants. But then you're driving through, and it might be nitrogen, it might be some form of pneumatic actuator. But some of the simplest control valves are actually more about force balance on a diaphragm. So they're not quite as, in a sense, it's a bit more implicit than this would show. But there's electromagnetic, so what they call I2P controllers, current to pneumatic, and then you've got to have a think, what happens if I lose my current? Do I want to lose all my pressure? So you can get them that are a bit like stepwise, so if they lose a signal, they'll hold their output. So you're often having to think of what happens if something fails, what's my next level of protection when you're designing the whole system. So the most common algorithm, certainly in let's call it the classic process industries, is the PID controller algorithm. If you were designing a jet plane, you might be looking at much fancier fly-by-wire things, and talk a little bit about stability. Well, some jet planes are almost like designed to be inherently unstable, so they can flip them around. You probably don't want to flip a gas or oil refinery around in that way. So it's certainly the most common form, and you can get them as almost like pure analog, or digital controls, basically a computerized version of it. And we've got the three terms. So P is proportional. So we'll say more about each of these terms and build up the algorithm. Or sometimes you'll talk about, there's different phrases: gain, proportional band, integral, or sometimes reset control, derivative or rate control. And you may use one, two, or all three of these, depending on the nature of your process, and they all contribute something to the nature of the control. So proportional control is the easiest one. It's simple, direct amplification. What was my error? Multiplied by a number, that's my output. Now, you've got to be careful. You can't just keep cranking gain up, because you might end up with an oscillatory or even an unstable process. So your valve going 0 to 100% open, back. Now, one thing is that because to have an output of non-zero, it means by implication you've got to have an error that's non-zero. So in principle you can never quite reach your set point. You have an offset. You can try and overcome that by having some form of bias or reset, and which is probably easily explained through the diagram on the next slide. But it is one of the disadvantages of proportional control. It's nice and simple, but doesn't get rid of all your error. So what the controller is doing here, so we've got our set point, measured variable, and error, multiply it by that, and then it talks about you now have a bias or an offset. So if you know what the output wants to be at a particular place, if you needed 50% of output with zero error, you can add that on. But as soon as you move away from that, the basis on what you've set, that manual bias, again you'll have some error. You won't quite have the measured variable equal to the set point. Alternatively, sometimes it's described as proportional band. must admit, in my days, I never really tended to think of it as proportional band. I much preferred to think of it as gain, and particularly like gaining so many million cubic meters per percent of valve movement, because then I could understand what the process was. But in what this does, I suppose, in some way, it sort of normalises the way you'd think about all controllers. What you've got to understand is it's described as a percentage. So the bigger the gain, the smaller the proportional band, which is, I never found intuitively obvious that 4% proportional band is a very high gain. That's a big number, high gain. But it's still used in many cases, because the reason it's big gain, what that means is you would get a lot of change of output driven for a small error, so which is a high gain system. So now what you can do, attempt to do, is if you increase your gain, in principle you would get closer control, but you'll never get to zero. So as we said before, we can add bias or manual reset to try and remove it, but integral action is a more refined option. But just to the slide build-up doesn't work too cleverly. I don't claim to be a PowerPoint expert. So what I've done here is I've created a system with some dynamics to it, and then put a controller. So with gain 1, you can see, right, okay, exponential rise achieves value, but we've got quite a big error here. We've got basically 50% error on that. Increase the gain to 10, faster response, smaller offset, but still an offset. Now fortunately, this system has very simple dynamics. If it had more complex dynamics, higher order, and was of itself perhaps naturally oscillatory, increasing the gain might be unacceptable. So what integral action does is it automatically reduces the offset, and if you get it right, it will be continually reduced to zero, and you can use it to help up some of the dynamic response. However, some slight downsides to it. It can increase overshoot, so it depends how important, when you make a process change, are you worried about overshooting, or are you worried about how quickly you achieve final value? And it does make things more oscillatory.
Overshooting means spiking it.
Well, oscillatory is swinging, so ultimately, in mathematical terms, it starts to look like an exponential growth. Now, in a real system, eventually something will hit a limit somewhere. Either a valve will have gone fully open, so it won't keep growing. But you don't want a system that's going like that. And I've seen regulators that are twanging away like that, hunting, and then that creates other it's not just it's bad control of your pressure. You see your whole pipework moving, and you get I think probably if we went back 30 or 40 years ago, there were instances of weldolets fracturing because of vibration due to poor control.
And due to the services, you always have that kind of signal. It won't be a straight line.
It depends on the nature of your process. If you have some time delay in your process, that is something that tends to make things unstable. So in other words, well, in fact, I think that example, let's see if I can go backwards. No, that one doesn't. One of the next ones has some time delay. So in other words, I make a step change and it waits a bit and then responds. So time delay. That, combined with feedback control and too high a gain and too much integral action, can lead to instability. I'm describing things here very much in what I'd call like time domain terms. So it's how things progress with time. If you were looking at it in frequency domain terms, your time delay introduces phase lag, which can make things unstable. Integral action also introduces more phase lag, and that can destabilize things. Derivative action helps in the opposite direction. However, there are some downsides to derivative action. So, but it is. But essentially, what a PI controller, this is one version of it. So what we've got is a set point, measure variable, and an error going into proportional. But we've also got this thing here. So what it's doing is it's integrating the error over time. So it's building up that, and an integral can have a nut. That can be 0, and you can still have a non-zero value on the integral of error over time. So you can get a positive output with a 0 error. So it integrates the error out. And so that's an example, but it's made that particular process more bouncy. Some of this is probably better illustrated on when we talk about the Ziegler-Nichols tuning rules. Okay. Now, derivative answer, because it looks at the rate of change of the error, can, once it starts to see the error move quickly, can slow down the controller output and reduce overshoot. So it's often used to reduce overall instability. Quite common with temperature control loops. So at one time I worked on an LNG vaporizer control. So we were regasifying LNG to come back into the grid, but there was quite a time lag on it because you chuck some heat in, but it takes time for the thermal effect to get through. So derivative control was very good for that. However, it can introduce noise into the process because you're taking the derivative of signals. If you've got a noisy signal, you'll get the first derivative of that is an even noisier signal. So particularly things like flow control signals have often got a level of measurement noise on them, and derivative action applied to that creates spiking. So I think that so if I try put nothing to scribble there. If is there a pen for that board? Let's see. Oh, I have made the mistake of using a permanent marker on someone, and it comes off. So what I'm talking about with measurement, so if I've got a flow signal might have noise like that. Now if I take the first derivative of that, say I'm doing it between there and there, I've got a change like that. Between there and there, I've got a change like that. Between there and there, I've got a change like that, and it tends to pick up that measurement noise. Temperature is often a more slow, stable moving thing. You can apply some filtering to it to try and get the noise out, but you've got to be a bit careful, otherwise your valve is then being asked to move in line with the measurement noise, and you soon won't have a...
So for the temperature control, this is derivative action.
Well, it depends. If you've got delay in it, you would often look for derivative control, and a lot of temperature processes do show some delay in them.
So the pressure and the level?
Pressure tends not to, because you open your valve a bit, you get a bit more flowing, and your pressure will start to rise close to where you are almost immediately. However, if you had a boundary pressure control where you're taking your measurements, let's say you were taking it 30 miles away, your pressure doesn't immediately rise, so you do have some delay in that loop. So you've got to be a bit careful about applying it. But that's probably a relatively slow moving process, and so you can tune up perhaps using PI control anyway. And again, if I was using a compressor, I wouldn't necessarily want to be asking it to make lots of small changes in speed up and down. So I must admit I've never actually come across anybody using P plus D on its own, but in principle you could do.
How easy is it to set those parameters, K parameters?
Well, that's where we'll talk about the tuning rules, but it can be difficult. So the Ziegler-Nichols rules are almost like operators' rules based on experience and looking how the process operates, but it also means you are operating with the process. In some way, if you've got a complicated process, you might try and model the dynamics first and then do it an offline exercise. So you've got a pretty good idea of what it's going to be before you actually ever go onto site. So again, some of the first boundary control systems we modelled using a fairly sophisticated simulation package and tuned up the controllers on a simulation first, and then said, right, here you are, these are likely to be about the right settings, but based on it's a 40-mile pipe and here's a set of differential equations that model your gas flow, but you wouldn't precisely know the exact time constants of things like your compressors, so you might have to do some fine-tuning, and I guess those who do it regularly probably learn how to, I want a bit of that and a bit of that.
And from your experience, how good did they tune to the industry, those controllers?
How
Good. And just, you have so many of them,
yeah.
and each one, to tune each controller will take time, isn't it? It's
Yeah.
not easy. They are all in the industry currently.
Yeah.
Are they
But-
all tuned like...
Yeah, I don't know how well they're tuned. I know I went on site with some sort of tail end of my time at engineering research at ERS, so they were trying to tune something up and they didn't have a feel for it. So because I had a bit more experience, I was able to tune it up. And the problem with that one is it was quite a slow loop. So it's all very well if you can go, right, well, it changes in 5 seconds, so I can adjust it and try it again a minute later. But if the natural settling time of something is half an hour, although you're talking about big pipelines with large volumes to get that. So if you're just looking at a very local control loop, but the LNG vaporizers were quite slow because they had a lot of thermal lag in them. So you make a change and it takes quite some time for it to resettle. So derivative actions can be used to stabilise out, but if we go to the full PID algorithm, again there's different forms that they can have. So-called parallel form. So effectively, so you've got a gain and a gain and a gain there, and you've got derivative, proportional, integral all being added together. Or you can think of it this way, where you have a single gain value and then think of those as times. Essentially, mathematically, they're equivalent to one another. So when you're tuning them, you've got to think, well, what's your real goal? Is it to get within a certain percentage, settle within a certain time? Is it but can you accept overshoot, or do you need it to approach effectively from one side? Obviously you want a stable process and you don't want sustained oscillations, but you've also got to look at what you're asking your controlling device to do. Say, I've got very good control but my valve's doing that. Well, trial and error. So Ziegler-Nichols has survived over the years. It does assume, in a sense, a certain type of dynamics in the underlying system. So I think if somebody were trying to tune, again, a fly-by-wire system for a jet aircraft, they wouldn't be using Ziegler-Nichols. But for many process systems, fine. And modelling and simulation, if you've got the information and you've got the time, yeah, you can do a full dynamic simulation, and there are packages around to do that sort of thing, and then you can have at least come in with a decent estimate of what your parameters might be, and then maybe fine tune. So we'll talk a bit more about Ziegler-Nichols and then perhaps 10-minute rest. So two types, closed loop. So you set your integral and derivative to 0, so you're in a proportional control, and you start to crank up the gain till it just starts to oscillate. That might not sound like a very comfortable thing to be doing, because what you're doing is starting to increase the gain till you get a certain level of oscillation. You can measure the oscillation period and then feed into equations. So it's a bit like a recipe. And so if you are, so the gain that you've increased it to is this critical gain here. So what Ziegler-Nichols would suggest, if you were going for proportional only, go for 50%. I'll say that I've never closed loop tuned a Ziegler-Nichols closed loop Ziegler-Nichols thing, because you just don't like the idea of sending something unstable, or control and integral action, or PID. So what I've got is an example here. So I've created a process. And so when I was talking about delay before, it's that sort of thing. So we've made a set point change there, but the system itself hasn't started changing until some seconds later. So that delay of itself in a feedback system can produce oscillations and instability. So tweaked the gain up to about 3.75, and then basically measured the here to here, this period, then plumbed the constants in, and it gave you that sort of response. Now you can see that using the rules, it's giving you some overshoot. So Ziegler-Nichols doesn't give you no overshoot, so you've got to bear that in mind if that's what you're going to use. So basically I've plumbed the numbers into the formulae on the previous table. So that was my gain, 3.75. So for a proportional plus integral controller, 0.45 times that gave me a gain, and that was my integral gain. And I say in this particular case it was that implementation of the controller. Open loop, slightly more comfortable one. So what you're doing is putting a small, you've not got your controller in the loop, you put a small disturbance in, maybe I'll move my valve by 5%, and then see how the flow varies. And you're interested in this delay time again, and then you've got this rise time here. It gives you an idea of the dynamics. So you're basically taking that line up there and estimating another time constant, and you're also interested in what's the so the gain is how much did I change the input, how much the output changed for a change in input. So if I move by 5% and it moved by 1 million, well, so I've got 20 million per 100%. But I can do that. You don't need necessarily. It's got to be a big enough change to be measurable and discernible beyond the noise in the measurements. But you can keep it controlled. You can operate within well-defined parameters. And again, then it's simply a case of plug into the table, and it's taken. And you can see that effectively the gain is taking into account the process gain, which seems natural, and also the sort of time delay and the time of rise in the process itself. So again, I think this was the same process, but this time I've measured that delay, I've measured that rise time, input step size 1, output has to change by 1. In this case, process time delay was 25 units, process time constant was 50. Plug it into the controller and get a response. But again, it is an underdamped, slightly oscillatory response. Life can get a lot more complicated. So they were what we call single input, single output controllers. Life can get considerably more complicated if you've got a multi-input, multi-output system, and people have dedicated masses of mathematics to this, to which I don't intend to expose you. But it does get considerably more complicated. So an example might be, so we're an LNG flow control system, but if I introduce more fuel into one vaporizer, that starves another vaporizer of fuel, which feeds around to a temperature. So what you've got is you've got cross-thread interactions between different controlling elements. So it's a deal more difficult to handle that. So I don't know. No. I'm quite open. If you want me to basically just keep on going and finish it as early as possible, or if you want to. Yeah. Okay. So we'll have 5 minutes, and then we'll go on to some components.
I just want to ask you. You mentioned that you could tune your controller with the computer to find those
simulation.
Yeah. How do you obtain the process itself?
Well, for example, the pipeline itself, its process dynamics are fundamentally to do with its size. So your model will, if you've got a proper model of the pipeline, those dynamics will be in that model.
Yeah.
Now, for things like how fast, it can be that certain dynamics can be neglected, because if your valve moves in a second and your pipeline dynamics are of the order of 1,000 seconds, your valve, and you're interested in the flow and pressure in the pipeline, your valve dynamic of 1 second is almost negligible compared to that. If there are orders different, it's almost it. Whereas if you were doing the valve movement loop on its own, then then it's 1 second.
It is.
And unfortunately, real processes don't come neatly stamped with a time constant.
I'm just wondering, will operator will allow you to do those, like change the set point and see how the system responds? So you could.
Well, in some, yeah.
Will they?
Well, that's why you've got to. Yeah, you've got to be clear what's acceptable within the process. If you can do it within the normal safe operating limits, so you're not overriding. Generally, you will have separate safety systems. So, let's say I'm trying to control pressure between there and there, but I've got a pressure trip there and a pressure trip there. So I'm operating in its normal limits. I don't override those, so I don't inhibit any safety systems.
Okay.
But they'll want to see that in procedures, and they'll want to know what to do with that procedure.
Because they're basically allowing you to control basically.
Yeah. So they'll want method statements, they'll want non-routine procedures which lay down what. They might say, well, I can accept a 2% change, but 10% no.
Is it always required to do those checks, to do those, see how the system responds to the set points, difference, in order to tune your...
And it might be that in some cases, if people have tuned up almost like identical equipment, they'll start from there, and then what they'll do is fine-tune. Right, this one's a little bit too oscillatory, so I'll just take the gain back a bit, because maybe this valve is a little bit faster. I mean, at times we did do frequency response testing on valves, so we had an idea of what some of these things were. If you wanted to model them, and you might take, and it might be from a test bed, so it's not necessarily in a live plant environment. But people can model things like heat exchangers. They can model,
reactors,
distillation columns, and so on.
Distillation columns are very complicated.
We did one in.
So you have so many outputs, inputs.
Yeah, but I think there are. They can do all that sort of thing on HYSYS. I've not used HYSYS myself.
HYSYS can do many things, but I don't know whether you could do the control with HYSYS.
I don't know. Well, but even if you could sort of, in a sense, model it, and you can go, well, so now I know what its dynamics are. Then take the dynamics and plug it into, say, something like a MATLAB.
Yeah, the MATLAB has
all.
Probably.
So in a sense, you're sort of saying, use the process simulation to get some, and treat it as a black box now. So I've got, from a MATLAB point of view, it's a black box. I've got an input here, an output there. I've got some numbers from a proper process simulation that is able to, you put in all your volumes and what the detail.
Right.
So, but
can I ask you, which company you from?
I'm currently what is commonly called retired.
Oh, retired. Okay. Which company did you work?
I used to work for National Grid.
National Grid.
So it was the whole flow through. British Gas became Transco, became National Grid. Transco became National Grid.
So you were part of the process and distribution, that department. Did you have that department there?
Well, in the end, I was actually in the control associate. Well, at one point, I was on shift in the control room, so we were forecasting the gas demand. We were sending the controls out to all the sites to say, right, flow, go to this. Set this pressure up as this, fill this holder now, do that. Monitor for alarms, send people out. And then finally, so in the last job I did a lot of liaison with the upstream operators. So that's why I could throw a few upstream examples into this. So for a time I was dealing with Gasco. So I've been over to their control room and I don't say a lot about gas quality measurement in this session. I suspect probably ought to say more about things like calorific value measurement and.
There would be a delay in that. It's not that. It doesn't work very quickly.
Well, the problem with some of the gas quality measurements is that they can be slow update.
Yeah.
Well, for accuracy, you can get faster inferential ones. So you with from a property. So for fiscal purposes, for example, you want to measure the CV. Typically, you're talking about chromatography, and you're probably talking about 3 to 4 minutes update between consecutive measurements.
Even the chromatography takes time. I just have experience on
chromatography. And I think when they tried to commission some the flow control on compressors. And they put ultrasonic flow meters in. So they're good, they're accurate, they're stable. On the other hand, you get a reading, and that inherent delay gave them problems with instability of the flow control loop.
Sure, yeah.
Because it was only updating every X number of seconds, whereas if you were using an old-fashioned orifice plate, you can measure that many times a second.
It all depends on your process.
So with some of the instrumentation, are using it for control purposes. So maybe a flow that's within 5% is perfectly fine for you. If it's fiscal purposes and business purposes, it's better than 1% and 1.1% on energy, because by the time you multiply it by the amount of money's involved, you're talking about some very big cash flows.
That's true. This error.
Well, I mean, there's been individual errors that have been cashed out in the tens of billions of pounds. Now, what it tends to have been, it's just that it's not that somebody's underpaid and somebody's lost money. What it's done is it's not been quite allocated across the system correctly. But if you went up to St Ferguson, where the Norwegian pipelines, you'll find that both the UK government and the Norwegian government are very interested in the accuracy of those meters, because then taxation revenue derives from it.
Sure. Yeah.
And I guess that's probably the same in many parts of the world. Then you've also got multiple partners. Upstream, you might have a principal operator, but you find that most fields have multiple ownerships. So 50%, 33%. No, and then they'll have complex commercial arrangements with allocation agreements.
So accuracy is very important.
Yeah.
Yeah. Thank you very much.
So, but don't probably. If I had been revamping this quite a bit, I might have put in more about some of the gas quality measurement side of things, because that's fairly generic. And in a sense, as a pipeline operator, you are probably quite interested in whether you're getting sour gas in your pipeline or not.
So you could get all the composition of the chemical composition of
well, there's different ways of doing them. So to take hydrocarbon dew point as an example, I think there's two principal ways. You can do a full chromatography, but you need to probably get up to C12s. So carbon 12, long chain carbon.
I did some.
And then use equation of state and infer it. Or you can use so-called chilled mirrors. So what you do is you pass the gas across a mirror, slowly cool it down, and when the dew just forms, that's the dew point.
How quick is that?
I think they're typically fastest ones are 4 minutes. A C12 can be about 12 minutes. However, if you combine a C12 and a C6, you can do faster.
We have some of them in university, chemical school.
Yeah.
They take ages.
Well, they're lab-based. The other complication, we're talking about field-based here, aren't we? We're talking about... Well, the thing is, it's not as nice an environment as a lab. You're not going taking a sample away, doing it there. And now you can't say that one is precisely accurate. And they need to be accurate across a range. So they'll compare them. The exercises were done to compare one with another, because the problem we used to have is we'd say your dew point reading is X, and they'd say, no, it's 3 degrees lower. Our reading says it's in spec. Your reading says it's out of spec. So there were some studies done taking known gases. So you take a very precisely produced bottle of gas, stick it on that one, get some reading, stick it on that one, and they were both they're both accurate to within a tolerance. But when you're starting to argue about differences of a bit less than the tolerances, you can have some quite interesting operator-to-operator discussions. If we're saying no, you can't flow because you're out of spec, and somebody's saying no, I'm not out of spec, I can't shut off my process now.
Nobody wants to.
But hydrogen sulfide can be done quite quickly.
How would you do
hydrogen sulfide? Well, there's different ways of measuring it. So you can, the old-fashioned way was almost like lead acetate tape. H2S reacts with that, produces a dark mark that gets detected. But there's
the exact what is the composition? What is the exact functions?
Well, you tend to do all the things. You tend to have a whole set of analyzers. So you'll have a water dew point detector for water content. You'll have an H2S measurer for that. Then separately, maybe a chromatograph.
Okay, what would you do if you take the measurement and you see there's a high level of H2S?
Well, potentially, because there is a legal limit to what can be transported in this country. So, and the commercial agreements reflect those legal limits. So initially, it's usually you've gone out of spec, start closing down. Well, you set a warning. It does.
It does.
Oh, yeah. Well, the process that's removing. Okay, in some cases it's inherently not there. If you went to, like when I was showing Southern North Sea, that dry gas doesn't really have any sulphurs in it, so it'll never go out of spec. They're not doing anything, they're not having to do anything to it. Northern North Sea, gas being associated with oil, will have more, and of course that's been, so what they have is various process plants to remove it. But of course that can change, and often what happens is, okay, the shore operator has set up his process to deal with a certain amount of H2S, if we use that as an example, one of the upstream operators turns on a sourer field and doesn't tell them. So a slug arrives, and before they can do anything about it, they've seen, oh, that goes up. No, okay, they'll turn the processing up and start to remove it. But by that,
So H2S is quite important.
H2S is a bad thing.
I see CO2.
CO2. In fact, there's not even any commercial limits on it now.
Wow.
On new agreements, because indirectly it would be limited, because if there was too much CO2 in it, it would
Especially if you have water in the
it
pipe,
would start to cause problems with the wobby, so the gas wouldn't burn properly. But you would limit it based on the so-called wobby index, the way the flame burns, not directly on the CO2.
Why I'm saying that?
So some of the biomethane that's being produced now, the small amounts of biogas, typically waste plants, well, that can have quite a lot of CO2 in it.
Because CO2 could get dissolved in water if you have any water
Yeah.
traces in
The salt cavity operators don't like CO2 because what they say is the CO2 then dissolves in water,
Yeah,
and they've used
yeah.
it produces carbonic acid,
Carbonic acid, true, yeah.
which then can cause corrosion in the
Yeah.
and what they do, but they have dehydration plants, so they are removing water because they're not allowed to give us it.
Yeah.
So and over time it just dries out. So the likes of Hornsey, that's been operating for 25, 30 years, I think is as dry as a bone now. Because they don't introduce any more water into it over time. So over time you're cycling the gas in, and each time a bit of water was coming out, and over 25 years of operation. But the newer ones to start with. But also when people are commissioning new pipelines, sometimes you find there's still a bit of water. So on first flow you get a big.
Because of testing, yeah, you're hydro testing.
And we've had that said, no, you will get that. And they go, no, we're okay. So Langelade had to flow for 3 days.
Wow.
You were talking about, well, at that point it was Sleipner to Easington, which is 600 miles of pipe, I think. But once it got a good flow, the water dew point fell quite rapidly. Water isn't generally a problem. The old gas holders used to be more of a problem because they were water sealed, so they could put water in. But the issue there was more that it lowered the calorific value, so the customer arguably was paying for some water.
Because those, if the dew point changes, you have
Retrograde condensation, and you get the waxes.
Slag from slag could damage your valve.
So I've seen filters that look like they're a chip pan dripping because there's so much rich stuff coming out.
Yeah, because gas move very fast. How is the speed of the gas?
Well,
more than 24 meters per second.
Yeah, well, only in the installation. Typically, when it gets reduced and going through the salt pressure installations,
high pressure.
But in the actual pipelines, they're probably averaging. I did do an exercise where I took a simulation and looked at the speed of every pipe in the UK, and I think it was a lot of it was only in the 1 or 2. It was quite low. It's only in the 1 or 2 and 3 meters per second in the majority. Because where you've got a lot of gas, you've usually got big volume of pipe, and high pressure, so the actual velocity is low. But they have the 10 metres per second for unfiltered gas, 20 metres per second for filtered gas limitations, but usually those speeds only tend to occur actually in the installations themselves, pressure regulating installation. So you've got a 48-inch pipe will come into something with 24-inch valves, and it's the say interstate pipe work will see higher velocities, but they've usually got filters on there because they're protecting the valve seats. You don't want erosion of valve seats. Okay, right. Shall I assume that anybody who wants to come back has come back? Right. So control valves and actuators. I'll try and. Yeah. So talk about simple diaphragm valve. So, simple diaphragm valve has a spring, and this, so it's spring loaded. So if you look at your gas meter, it's got a little regulator on it. So regulator, governor, control valve, sometimes all interchangeable terms. But there's a little pressure regulator on that that's controlling the pressure just before your gas meter, and that is a simple diaphragm valve. So it has a spring, which, and the stronger that spring, the bigger the gain in the system. It's got a feedback, which is the diaphragm. I'll show it diagrammatically, I think, in a minute. Depending on how you screw the spring in, you've set your set point. So if you wanted to change the pressure on a low pressure district governor, you wanted to increase it by a couple of millibars, you'd be turning a spring, not downloading a computerized set point. You've got to think about the failure mode. So what happens if something goes wrong? Is it more important that it fails shut, i.e. protects the downstream system from high pressures, or is it more important that it fails open, i.e. doesn't starve customers of gas? And it'll modulate things by controlling the flow. So some examples: so piston valves used at high pressures. There's a thing called the axial flow valve, which is used a lot in the UK, which is sort of more at the medium pressure end, and then these diaphragm valves at medium to low pressure. So this is an example of a piston valve. This was a high pressure valve that was developed at the engineering research station, and then sort of produced commercially, because there wasn't particularly anything on the market that did that sort of duty at the time. The most common one I came across, and there were at one time sort of hundreds, if not thousands of them across the UK gas system, was this axial flow. And it's actually a very simple one. It doesn't have any real moving parts, so it tended not to fail a lot. And it sort of works by, there's a cage and a cage, and this sort of rubber sleeve boot here, by applying pressure to either side of it, can allow more gas flow through or reduce the gas flow. But it doesn't have like a piston that moves up and down. It was, and I did hear once of a story that they discovered one of these had got damaged, so they just turned it inside out, and it carried on. No, they were able to effect an immediate repair till they got a proper replacement. So they were very robust, but you had to be careful about things like the rubbers. This is a simple diaphragm valve. So we've got, there's the diaphragm spring loaded here, the set point. Slightly bigger one in operation, but essentially it's no different to that previous one. But in many cases what you'll find them is there's multiple instances of them. Again, the higher pressure you've got tends to be the greater the levels of redundancy built in. So if you look at say a distribution governor, it might just have two streams in parallel with only one valve in each, whereas you get to the higher pressure, you've typically got two controlling ones there. So that's the one that's normally operating. If that fails, this one's got a slightly higher set point, so pressure rises, this starts to control. If that fails, this will close down, but there's a parallel, you can just about see behind, there's an equivalent parallel stream behind, so you've got redundancy against failures open and failures closed.
Question, please.
Sorry?
I have a question, please.
Yeah.
Yeah. I'm thinking if all these valves try to reduce the pressure,
Yeah.
coming to ensure that we measure the gas flow
Yeah.
very well. How do we ensure that we are not losing so much pressure at the end after the valve?
Yeah. So typically you've got your different pipeline pressure designed to pressure regime. So let's say I've got my national system here at 70 bar, and I've got my control installation there, and this is, say, a 38 bar. So what this one might be managed from a central control room. So the sort of job I did for a number of years when I was based over in Killingworth, what we were doing was looking at the gas demand, forecasting it, and then monitoring what had actually occurred, and then we might adjust the flow on here, say from 5 million a day to 6 million a day, and looking at how that pressure was varying. But this has been designed, and this has been, no, that was designed. So the pipeline's designed, and then your pressure installation is designed to limit the possibility of that running above 38 bar. But this one's quite a managed system, so I'll talk about SCADA systems and so on, so control rooms and monitoring. But the vast majority of these installations, so like the installation in there probably has no remote monitoring, so it just sits on a fixed pressure all the time. So they're saying, right, so what we've got is a 7-bar main coming into the outskirts of Newcastle. Here's my installation. I've got some controls here, so I'll say some control valves. So this is a 2-bar system. So this is my normally controlling one, so I'll set that at 2-bar via the spring setting, or the spring in a pilot here, and it stays fixed. So it sits at 2-bar, and it's just trying to hold 2-bar in that system. And 2-bar, the planners have looked and said 2-bar is enough to meet all the possible demand that can occur in that downstream system, even on the coldest. Well, at distribution, they'll look at the coldest 6 minutes at peak in the winter. As you start to come back up the system, it might be the coldest hour, the peak hour. On the big transmission systems, I'll look at the peak day, and it should be able to cope with it. Now, if it can cope with the peak day, it should be able to cope with anything below that. But then this one then might be set at 2.1. So if this goes open, then this one comes into control a little bit higher. But it's so that might be the normal limit, but they'll say, right, well, the absolute limit on that is, say, 2.7 bar. Then this stream here is staying closed most of the time, because this is your standby stream, so I might set that at 1.8 bar. So if one of these fail closed, pressure starts to fall, but at 1.8 bar that'll come in. Then somebody might have to go out and do something about it, go and effect a repair. Why has this failed? But it keeps your gas flowing, and then just in case, we'll have another. We've got that one protecting it, say 2.1 bar. So if that fails open, well, you're still protecting that against going too high. So, but the vast majority are actually sitting on fixed pressure most of the time. Some of the distribution mains will have what are called clock controls on, now, because old-fashioned, certainly the cast iron mains, the joints in them have a certain amount of seepage, and one way of managing it is to keep your pressures as low as possible. So overnight, you don't need as high a pressure as during the day, so they might switch from one setting to another. And we'll mention that a little bit in terms of it actually interfacing to some of these things. But as they put more and more of the yellow polyethylene, if you've ever come across roadworks and see great big coils of that stuff, that doesn't have the same problem. So in principle, you would just set that at the highest pressure you need to meet your peak demand and leave it there. Why go and fiddle with it? So this is sort of a cross section of a fairly simple diaphragm valve. So what you've got is, so you've got this adjustment here that goes onto a spring loading. So that's your set point. So when they set that up and check it, they'll check that that's set to give them 2 bar pressure on the outlet. That's pushing on one side of the diaphragm, and then what you're doing is you've got, there's your valve mechanism. So if you move, if you increase the force on that side relative to that side, that will open, let more flow through. If as pressure starts to rise, that would start to be fed back onto here. So we're talking about a feedback mechanism onto this side of the diaphragm. Close that valve a little bit and reduce the flow, and therefore bring the pressure back towards the set point. So you establish an equilibrium that has this valve at the right level of opening for the flow that's needed to maintain the pressure at a particular time. But you can go a bit further. You can start, if you do need to control things, let's say manage your system more widely, you've got motorised springs. Again, a lot of those were used on the old holder stations, were the gas holders, where you might be flowing more gas into it during the day and less gas at night. So you were doing a lot more active control. So I suspect there's fewer of those about these days. But you also want to think, well, what do I want to do if my interface fails? It could be fail high, or fail low. Do you want to go open, closed, or is really the best thing to do to fail stay where you are? Don't move, so freeze fail. You can start to gas load onto the diaphragms to effectively. So what? If you remember when we used that diagram, there's a force balance here. If you start gas loading on that diaphragm, you're having the same effect as changing that spring setting and changing the forces on there to open that valve. So you can achieve a form of remote set point control there, if that's what you need. Say across the vast majority of UK gas distribution system, you don't need to change things. Now you don't overcomplicate and put more process plant in than there is necessary. So KC pilot, a lot of regulators then use pilot regulators as a way of improving the control. And that was a form of pilot with two diaphragms, and you could gas load one, and that can be, depending on how you load it, you can make it fail high or fail low. Or direct actuation, so you get more complicated actuators, pneumatic, electric, electro-hydraulic, with some form of actual valve position feedback. Failure modes, so again, fail open, so it'll jump to some pre-set high level. So typically something feeding a local district heat, they may prefer for it to fail open because they haven't got a particularly high pressure coming in, and the problem is that UK houses don't have safety devices that shut when pressure falls. If pressure falls to your house, if your cooker is on, it will go off, and then when the pressure comes back on, you've left your cooker on. So there's no inherent safety in houses, and the gas safety management regulations tend to focus a lot on domestic safety for that reason. So really you don't want things failing closed a lot, because you will then create risk to the public. Alternatively, it might be that really the safest thing, so I think we were talking about gas quality measurement. So let's say you have a sour gas feed, high H2S in your gas, and you don't want that to get in your pipeline because you worry about stress corrosion cracking. In that particular instance, you'd rather lose production and protect the pipeline against integrity issues arising from H2S ingress into the system. And fail freeze, it'll leave it where it is, but you might need to put some extra high pressure, low pressure protection. Valves themselves can have different characteristics. So you get so-called direct acting, so the more you increase the input, the valve will go further open. So if it was, let's say, a 4 to 20 milliamp electric interface. 4 milliamps is closed, 20 milliamps is open, but you can have it the other way around. 4 milliamps is open, 20 milliamps is closed. So so-called reverse acting. And I've seen that confuse people. Why is that? Why is that working in that direction rather than that direction? Also, what comes into play is so-called linearity. So, linear valve, effectively, if we refer back to our Ziegler-Nichols discussion, the gain is the same at all points. So, a 1% movement of your valve will create a 1% change in flow. But many valves are different to that. So, so-called equal percentage valves have a characteristic that probably looks. Oops. No. So low gain when nearly open, low gain when nearly closed, and high gain when nearly open. Quick opening is the reverse of that. You get most of the flow in the first, let's say 80% of the flow for the first 20% of the movement. So diagrammatically, a bit like this. So this is your linear valve opening percentage against flow percentage, nice and linear. This is your equal percentage, so it's sort of like an exponential type of relationship, and then that's the reverse. Now, if you're thinking of, if we go back to Ziegler-Nichols, that was a lot based on process gain. So if I do a test with the valve here, I've got a different process gain to when I do it here. So there are some strategies that can be adopted in the controller. So you might do some gain scheduling, for example. So when my valve is 20%, I'll apply one gain value. When my valve is 80%, I'll apply a different gain value. Again, there's been a lot of work done over the years looking at fancy adaptive control techniques and a so-called self-tuning control, but a lot of that has never been really adopted by, let's say, process industries. But adaptive gain is one that I think a number of just simple commercial controllers would offer you, so you can gain schedule across the process. Interfaces, so I to P, I current, P pneumatic. So might be some places it's nitrogen, but again that's probably where you're talking about bigger process plants. So if I went on to a producer side, they've got a multi-million pound complex. If I went into a distribution governor house, no, it doesn't have lots of, you wouldn't have a separate nitrogen supply in there. In fact, they'll try and use gas as the actuating mechanism and just basically dump gas into the downstream system if they can. Problem with some of these I to P converters is they will vent continuously. There's a continuous flow out, so then it means you've got to deal with and you are talking now about electricity in potentially explosive atmospheres, so there's protections that you've got to apply there as well. Stepper motors, not sure whether there's, I think historically at one time there was quite a lot of those in the gas industry, more associated with gas holder stations and this is an example of a control valve that's got an external controller and then a position actuator. So it's actually, as you put a current pressure loading into here, that's moving that valve up and down and controlling its position. So I think when I did a job looking at the LNG fuel control system, it's a big piece of process plant. It'll have more sophisticated controls attached to it.
Does the color code vary from places for control?
So this is, I suppose, is usually where you're looking at remote control and where you're almost having to look at some form of process automation. So you're trying to manage various bits. So there's a control room who are modulating this. So it might be nominations led. So if you're a transit pipeline, for example, you've got commercial nominations come in, saying we want this amount of flow here, this amount of flow here. So there's a control room somewhere that's saying I want this, but then eventually it interfaces to something like this that will manage the flows in the, let's say, within sort of national grid, stroke regional distribution systems. These will typically only occur at the off takes where gas is taken off the national transmission system, because it's the, if you wandered around Newcastle and looked at all the governor houses, and you probably would never find one of those. No, it's a level of complexity that's not needed. It would be more like a simpler one. So this was with like a motorised drive one, again probably used more on things like gas holder stations, so perhaps not a lot of those about, certainly in the UK these days. And again, because you're in a gaseous atmosphere, you've got to look at this housing here had to be flame proof. Now, because if there that's sort of an example, and you can see what so it's not particularly a complicated thing, but it effectively it's a motor that's winding the spring. Now it's a bit like having a maintenance operator and sending a message and saying, right, add another quarter turn on. I want the pressure a bit higher, or I want the flow a bit higher. So a fairly coarse sort of interface, but it did work with those sort of. So a lot of this was retrofitted to even older equipment. And if you're designing new stuff, you don't have to. Then you'd probably come up with neater designs than some of these. Some of this reflects the long history of the UK gas industry, and the fact that stuff was retrofitted onto older equipment. So you're looking at interfaces. So if you already had a standard control pilot, so a stepper motor that would wind that, is probably neater than completely rebuilding that control stream. So this is an example of a control pilot stream on. So that actually means that's the flowing stream. So what they're doing here, in fact the next diagram shows it a little bit better. So this is this. So there's a measurement here that's sampling the pressure, but you can also load the pressure on top of another diaphragm. So what you've got is an extra diaphragm, pressure load that, and you can achieve remote set point changes. And this was used, for example, with some district pressure management schemes where you were looking to minimise district pressures to minimise leakage. So you'd have a control system that would perhaps lift this during the peak of the day and the evening peak, and would drop it back overnight. But equally, that could just be done on a simple clock type mechanism, so something that switches from one setting to another setting, or there are electro versions of those around as well. So that's an electro pneumatic converter. Contrast doesn't show up well, and well, that's like an I2P controller in a cabinet. And again, because it's electric equipment in a gaseous area, so you've got to look after. In this case, I think they adopt an intrinsic safety approach. So what you do is you minimise the possible energy that can occur. I don't know if you've ever noticed, sometimes if you switch a light, sometimes you can generate a spark. So if you get an open circuit, so what a safety barrier can do, it won't necessarily stop it sparking, but it'll limit the amount of energy in that spark. And the natural gas is classified as creating an atmosphere that needs a certain amount of energy to create an explosion. So as long as you've got something in your electric circuit that will limit that amount of energy on, if somebody short-circuited it, you won't get an explosion. And then you get these high integrity pressure protection systems. So typically these are often at sort of boundaries between, say, an importation terminal and the national transmission system, the interconnectors. So things that are operating at quite high pressures, and you can see they're not only making one measurement, they make the same measurement 3 times and then do so-called 2 out of 3 voting, because you don't want to be, again, you're starting to look at what might go wrong with that pressure measurement. So you don't want to keep firing it shut when it's not correct, but you want to be sure that it will close in. And you might have more than one level of pressure safety. You know, and typically they'll offer 3 or 4 different levels. First level might be a simple alarm. The next level might be start to try and control. The next level might be shut completely down, because we've failed. And typically, there's a lot of witnessing goes on. So I think you've probably covered things like schemes of examination. So when new sites were connecting to the national transmission system, one of the things they were particularly interested in was the schemes of examination for this sort of thing. And both parties have a responsibility under the safety legislation for the correct operation and demonstration and testing and validation of these. So HSE would potentially pay a deal of attention to it, but it often was it's one of the last things that's done before a new supply comes on. Is there anything they can do to damage our system? And if you've got, the LNG terminals have, say, class 900 pipework, so they might have 140 bar lurking around within their terminal. The national transmission system isn't designed to that, so there has to be something that ultimately will protect us against a failure on their side, and it's the sort of HIPS. So HIPS is high integrity pressure protection system. So we'll move on to a quick gallop through sensors and transducers. So transducers and transmitters, the difference is a little bit academic really between the two, but what they are is basically means of converting typically pressures to some form of electrical signal. So you might get an analog signal, so it might be generating something like 4 to 20 milliamps, but it might also be a Modbus type, a digital value. There's all sorts of different types of ways of converting. A lot of them work on the principle of some sort of diaphragm movement. One to keep an eye on as to whether things are defined as being gauge pressures or absolute pressures. And equally, you might be interested in just a single pressure measurement or a differential pressure. So I think the subtlety between the two, typically transducers, a small device is just producing millivolt outputs, designed for small size, small cost. So you might find them out in local districts if they want to monitor pressure across districts on a small logger type device. It'll only deal with a short distance. Can be prone to a bit of interference, so you've got to do a bit of electromagnetic shielding. You need a regulatory supply, and then you build that into a system through some components. I think there's a slide that shows a picture of a typical one. Whereas transmitters, and if you're working on bigger pipelines and process plant, you're probably really looking at this sort of stuff. So it might be 0 to 10 volts, but more typically current loop, 4 to 20 milliamps. And one advantage found with that is if somebody actually breaks the connection, you can tell that 4 milliamps will give you 0, 20 milliamps will give you 100%. If somebody actually pulls the wires out, or rats get into your cable ducting and eat through the insulation and short things out, and rats quite like cable ducting because they're a very nice pathway and they quite like eating plastic on occasions. If it goes to 0, you'll get effectively a minus 25% reading. So you know the difference between a fault and just, it's genuinely reading 0 because the answer today is 0. So that's why 4 on 0. Better over long distances, so you'll find long cable runs, they offer better noise immunity, but you've got to do a bit of signal conditioning and electronics. But the thing is, they tend to be bigger, beefier things, higher cost. They may have local digital readings. I think most terminals I've walked around, they have an LCD display on them, so you don't have to radio back to the control room to find what it's reading. You can read it yourself locally as well. But again, there's an element of cost in there. So the advantage is not particularly affected by the resistance of the connecting wires. So you can operate over long cables. That provides the power to the transmitter. And I say the Live Zero is certainly an advantage and a bit more noise immunity. So, I mean, if you've ever seen an integrated circuit, this is a tiny little integrated circuit with a very small pressure transducer on it, and it's used typically in something like this, or a district pressure logger. And some of these can be used to also provide a level of pressure change clocking typically, but also for monitoring district pressures and performance. Have we got it set at the right pressure? And I think one of you was asking, how do I know that I've got the right pressure in the system? Well, you do have some monitoring via these systems, and let's say the planners had forgotten about that nice new housing estate that's just been added onto the end of the district, and you're starting to get low pressures. If you're monitoring, you can then send somebody out and say, we'll have to remodel that, replan it, change the set point a bit, and you can then monitor the effectiveness through something like that. Whereas transmitters can be bigger devices. And typically a lot of them work on this sort of strain gauge principle, so you're applying pressure, either a differential pressure or one of those might be open to atmosphere. It flexes the diaphragm, and you measure that change through a strain gauge, which then gives you an electrical signal which you can then convert into a pressure reading. There are capacitance based devices as well, but similar principle. You're creating a change which will change the capacitance, which you can then measure, and there's a defined relationship of changing capacitance for that device. There's a change in pressure. Tensiomic, and another one. Piezoelectric, so it's the reverse of your cooker ignition, where you press a button and you get a spark. Well, this is put a force on and you get an electrical signal. An optical, must admit I don't think I've ever come across an optical pressure transmitter myself, but my previous colleague who first prepared these slides obviously had at some point. You want digital, you've got your analog, and then you've got to do digital to analog conversion, and you've got to be careful that you're getting the resolution that you need out of it. So you need to understand what that is. Using 8-bit, 12-bit, 16-bit. You can get parallel or serial inputs. Field bus compatible devices are now popular, so you can, particularly I guess again on the larger process plant. Again, resolution, and your A to D converter does play a part in resolution. It depends how important resolution is to you. Flow measurement, two typical ways, so positive displacement or inferential. Again, if you're looking at big pipelines and process plants and production, you're going to be talking about inferential, not positive displacement. So positive displacement is typically like so your gas meter, the gas meter in house is a positive displacement meter, and so you get some medium pressure. So some commercial meters in the UK are diaphragm. But probably of more relevance, I suspect, to most of your inferential. So you're measuring a property, something like a velocity, or you've got orifice plates. So we'll say a little bit more about each of these in turn. Turbine meters, ultrasonic meters. It's not what I'm desperate for magnetic, so for conductive fluids only. So they're our old friend, the orifice plate. There's still masses of those. I mean, they have. They're relatively simple, apart from the fact you've got to have a carrier, you've got to have an inspection regime, and if you're using it for fiscal purposes, then you've got to be very precise in knowing the measurements of your orifice plate. Otherwise, you find that somebody is out of pocket somewhere. But essentially, as the flow comes through this orifice, you create a pressure differential. You measure the pressure, the differential pressure, and then if you're just using it for control or indication purposes, that might be sufficient. If you're using it for fiscal purposes, you need to know things like the density, the temperature, the compressibility. If it's energy, you also need to know the calorific value. You need to put in things like viscosity. You might need to know the altitude you're at, what the gravity is on the day, etc. When they do the full fiscal examinations, all those things. Fortunately, probably your gravity for your location doesn't tend to change very much. There's some nice standards to read on the if you're simple with that.
The orifice plate.
Mm-hmm.
What is the material specification of the orifice plate?
So I think there's things like you've got to be careful about the thickness. So you've got to look at the differential pressure you're generating. What you don't want to do is inadvertently create yourself a nozzle. No, if you've got fast pressure changes, so if they're close coupled to compressors where you're getting rapid changes, it has to be able to withstand the forces. You can look at thickness like that. I think the metallurgy, is just I've never really thought about the metallurgy itself. It's just the same. I think they're just usually stainless steel. But the size of the orifice will dictate the flow range. So a small orifice will generate a lot of dP for a flow. Bigger orifice is less. So you've got to size it appropriately. Otherwise, you start to generate too much dP, and you do get pressure losses across your orifice plate. So again, if you've had to put cost in to increase the pressure, you don't then to be throwing a lot of it away across an orifice plate, unless you, for some reason, are later on reducing it. But it is nice and simple. There's no moving parts to it. But you've got to keep the faces clean so they are inspected, and you don't want them getting hit by particles. So usually there's filtration upstream to keep them clean. A bit of oil just oil on the face, or liquids, hydrocarbon liquids, hence maybe dew point control, can cause inaccuracy. Turbine meters, some are used for fiscal purposes. Some power stations still have them, but some control purposes. Basically, you're spinning this rotor around. I'll have an index on the top, bit like your meter at home. So you can get a reading of what the volume that's passed is, but often you're also interested in the flow rate. So the speed of that rotor will give you an idea of flow rate. Thing with the orifice plate is you have to do some computation. You can measure your dP, you can measure your temperature, you can have other properties, but then somewhere you've got to plug all that into a flow computer. So that's an actual turbine meter with the head on it, and it will have frequency signals if you want a flow rate. Then I think increasingly more popular are ultrasonic meters. At one time there were certainly not that many used in the UK, but I think a lot of the new sites that we were seeing connected were using ultrasonic. Advantage, you see, nice free path. You're not losing any pressure across that. I think in the early days there was worries about other interference from other sounds. So if you were near a bend, for example, would you get corruption on on the measurement, but essentially it's measuring the velocity of sound in gas, and then once you've got that, you can convert that into an actual flow measurement. Trouble is, the electronics are considerably more complicated because you've got a number of heads. But it just give you some. If you've got heads all the way around, usually you've got a deal of resilience, and again, a lot of the modern ones will come with a condition monitoring software, so you can start to see if you're losing signals somewhere, cords somewhere. It's not really. It doesn't have problems with contamination like an orifice blade. Turbine meters are even worse. If something hits a blade on a turbine meter, it can damage it, and it's also very difficult to get out. So, for control, you're largely interested in you just want it to respond and it to be repeatable. You're not if it's just, say, generally controlling the distribution of flow across the system, it might not matter to within a few percent. Whereas if it's fiscal, you're interested in long-term accuracy, so you need ultimately proper flow computers with composition information and all sorts of gas properties. Don't say an awful lot about other measurements. So we've got temperature, calorific value can be very important, and often you'll have more than one chromatograph. Again, there's different ways of doing it. You can do a full gas density and an equation and infer the properties, or there are, for quick measurements, there are other ways of doing it. Gas quality, so WOBE, effectively the way that the gas burns, the relationship between calorific value and density, dew points, sulfurs and hydrogen sulfides and density, and so on and so forth. Components might be of interest. You might be interested in how much ethane's in your gas, is it? There are some suggestions that higher levels of ethane present risks to certain pipelines. And that's the instruments part of things. Final one is relatively short. Yep. Sorry.
We've looked at the meters.
Yeah.
Under multi-phase flow.
Right.
Is that something that you can concentrate? You can come up with a concrete workout, then maybe two on the physical meter.
Fiscal meters.
Physical meters.
Yeah, I would have to say I'm not a metering expert, so like multi-phase flow, because I've worked like in the UK, the onshore side of things. Essentially, you are transporting dry gas. You're not dealing with multi-phase. So unfortunately, I can't really say a lot on multi-phase flow measurements. I think that's quite a specialist thing. So, your question about fiscal meters?
Yeah, fiscal metering, the options, what would be?
Well, generally you'll find that most of the contractual arrangements don't say use this meter or that meter or that meter. They'll say measure to this accuracy, and the standards will say what you've got to do, and people will test them using, say, in a lot of cases they use Monte Carlo simulations to prove that they're accurate right across the range. But on the big sites now, you find ultrasonic is becoming more and more popular. It's stable over time. Orifice plates are still very popular, and the thing is, you can have spares. Turbine meters, the problem is if something goes wrong, and also they're probably better on steady flows, because if you've got something that's changing quite rapidly, a turbine meter speeding up and slowing down, the bearings can go on and have had problems with that. In the UK, gas is odorised as it enters the regional distribution systems, and it's odorised based on flow, as a proportion of flow. So the flow is not only forming a fiscal thing, it's forming a safety thing there. So what you don't want is a turbine meter that then will go and stick and not put any odour in your gas. Equally, it can interfere with the flow of gas into your system. So turbine meters, less popular, but I think one or two new power stations have still used turbine meters, because they're going to operate at one level, another level, so they might use they can design in a way that, like, it's doing one duty when I put my second gas turbine on, I also put my second turbine meter on. So they're doing a nice duty. Put something that's swinging around and moving fast. Turbine meters are not so good. Ultrasonics is a lot more computational power, but you can use that computational power for a bit of condition monitoring. Orifice plates, you've just got to be, you've got to maintain them. Again, if you're on probably a permanently manned installation, there'll probably be a cycle of, you might have 6 meter streams. You use up to 4 of them. The 5th one is under maintenance. The 6th one is your spare. So if you have a problem, you switch them round once a month and inspect and validate. And you inspect and validate all the instruments, and all the measurements you're making associated with it can also contribute to uncertainty in the measurement. There's a number of ISO standards that will tell you about sort of how to achieve uncertainty and repeatability in your measurements. But again, they're about the general principles. They don't go, this is better than that. It might depend on how much space in your plant you've got. Have you got long straight runs, or because acoustic fluctuations. So in the early days with ultrasonic meters, people were worried about acoustics from gas going around bends and through valves affecting the readings. They seem to have overcome some of those difficulties. Again, I think the signal processing capability of modern computers is considerably better than it was 20 years ago. Now you can do a lot more with it. But orifice plates also, you don't install a physical orifice plate close to a bend, because it will distort the flow pattern, because it is predicated on basically a nice flow regime, not a turbulent flow regime coming in. So there are one or two other, let's say, cheap and cheerful ones. You can use what are called so-called averaging pitot tubes, something like a tube with a set of lines, like a flute, and it will create a change in pressure as a function of flow. But it's more if you just want flow indication, not for fiscal or custody transfer purposes. You'd be pleased to know there's, I think, somewhat less slides in this one. Talked about sort of gas supply and pipeline systems. A lot of the previous stuff is at component level, so this is more sort of almost like this, then a step back again, almost like towards me in my control room role. So I'm monitoring a wider system, or control rooms or on a terminal or with a compressor. So a little bit, so PLCs, programmable logic controllers, DCS distributed control systems, SCADAs, supervisory control and data acquisition. And these days you've got data warehousing, data historians attached to them, and probably one might also argue in a lot of cases they feed data into commercial systems. So the UK billing system is indirectly receiving information from orifice plates. So an orifice plate measurement is made, figuring out what the flow is, that's passed to a SCADA system that then heads off into a commercial system, which then in the end is used to generate bills or invoices for the people who are trading that gas. So the PLCs and control are typically microprocessor based, so they will implement the control algorithms I was talking about in the previous session. Gone fairly. There's all sorts of hardware. All sorts of manufacturers will sell these sort of boxes to you. Some cases you can set functional software, sort of high level logic. You can do flow computations in your flow controller, so it'll might have some functional logic in there. Sequential control, so you could have do A then B then C. So in case of when I did an LNG vaporizer control, at first they said they wanted a nice continuous. Once it's on, we want it to control the throughput and the gas temperature. once they said it can do that, we want it to do the startup as well. So that's more of a batch type thing. Switch this, followed by this, then bring this on. So as it so happened, the unit we were using was able to do some sequential control as well as as well as straight PI control. So continuous control is the type we're talking about, the PIs. Some of them will do many loops. I'm not necessarily talking about multi-input, multi-output, but it might, you might have 4 flow control valves, and you can do all 4 in one controller if that's what you so desire. And this is an example of Eurotherm are a sort of well-known company in that area. This was simple flow control. It's like a modular box. It could slide into a cabinet, but it just does a single loop. It's got some a process display there. These buttons will allow you to put it into auto or leave it in manual, raise and lower set points. Look at what your set point is. It'll generate a few alarms for you if necessary, but isn't terribly complicated. Distributed control systems typically within a single site. Got higher speed data links, so local area networks, and a lot of closed loop control. Now that's not what we tend to see sort of in the UK gas industry. What it is it's lots of little process plants. This is probably more common. So if I went over the fence onto the producer's side, you'd see this sort of stuff. And sitting within it might be multiple controllers, programmable logic controllers. Probably the nearest I've seen on the national grid side of things are the compressor stations. So you've got multiple compressor units, and each compressor unit has maybe got suction pressure control, discharge pressure control, flow control, discharge temperature control, along with then a whole bunch of safety things that say switch off if temperature gets too high, exhaust cone temperatures and so on. That might look conceptually something like this. In my case, I'm more familiar with this sort of thing, like the SCADA systems. So we were covering large areas. In the case of my last job, it was anywhere from St Fergus down to Exeter, down over to Kent. It was the whole of Great Britain. So reasonably large area. But also some of the terminals do that. Some of them monitor offshore. I don't know if you've been to the Gasco control room in there.
I've done a DOV flow center.
Yeah. Yeah, but their control room is very similar to what we have in Warwick. So it's large area. It's gathering in data from all sorts of sources via telemetry, but it's relatively low bandwidth. So you're not doing things at the millisecond level. You're monitoring the broad health of the system. The local type control and safety is handled at the site level, where you've got faster update rates. But what you've got is an awful lot of data links. So you're scanning probably hundreds of different sites over a time. So it's more of a monitoring exercise. So you're not literally intervening all the time. Don't tend to find control loops. Now, the control loops are implemented at the more local level. But a lot of data coming in, and still the ability to send the set points out. So if I want to change the broad nature of the way the flow is moving across the country, I've got the ability by changing flow set points, and they get issued over communication systems to the site, which then does the local, the PID closed loop control we talked about earlier. So you'll have some form of central monitoring station, so lots of terminals, and actually usually lots of redundancy in here, and possibly even a second location. So if you have a fire and have to evacuate, or they're changing the carpets that weekend, now you've got somewhere to go. You can't not monitor a communications network. You know, at one time it tended to be a lot of point-to-point, what we call private wire, so 4-wire systems through the BT network, or maybe microwave radio, so to a point, and then microwave to microwave and microwave back to the control center. These days, a lot of satellite out there now, satellite communications, but again, still dual sighted. And then you've got your remote station making its measurements, and basically what I would call a remote telemetry unit. So a unit somewhat like this. So that's a base unit, and then you can put different cards in to deal with analog inputs, digital outputs, etc. Some of these now start to have some display functionality. The intention was to really try and have the same mimics on site as the control room have, because often the key confusion is I'm going on site to maintain slam shut A. I could only see slam shut 1 and slam shut 2 on my screen. So if you don't have the same understanding of what's on site, it makes maintenance more complicated. So having the same diagrams and looking at essentially the same data, it's a relatively recent aspiration, because in the end you're not trying to replicate a control room at site level, because you've probably just got a small kiosk with a bit of equipment there. That's the sort of thing that people are putting in now, and it's got redundant processing in, so there's a level of redundancy.
But the local site has safety overrides or safety lockout.
So the safety devices shouldn't depend on the communications loop, because communications can always go down. And in the early days of trying satellites, you could fairly readily track snow through the country as the satellite dishes filled up with snow. But also, like, something like that can interfere with the communication signal. So the safety's got to be devolved down to the site level, and eventually there is a non-electronic form, because what happens if your power goes? Okay, most of the sites have got a certain amount of power backup, like batteries that will last for 24 hours, but I imagine they had a lot of fun the other day when Storm Doris came through, because I was on shift one Christmas day and a storm had gone through the previous night. You don't really want to call people out, but we had power alarms on so many sites, we had to get lots of people out, because usually the power had returned but it had tripped the local site power up, and if you'd have left it, the idea was you usually have enough backup on site till you can get a maintenance person there. So 8 to 24 hours, they're not designed to last indefinitely, these sites. And but ultimately you tend to have the ultimate safety usually sits on something that's pneumatic, so it doesn't even rely on the power, so you've got levels of redundancy and safety. But so a control room will be scanning multiple ones of these, and it'll go, give me your analogs, give me your analogs, give me your analogs, and we were scanning typically 1 minute frequency. Usually you have a capability of looking faster, so if somebody's doing some maintenance work on the time and you don't want to wait till the scheduled update, you can either press a button and say give it me now, or say put it on fast scan, tell me every second for the next 3 minutes. You can't do that with all the stations though, because the systems aren't designed as high bandwidth systems. So it's like a pole, so the central system is the master and the outline system is the slave. It's relatively simple. It will go, so you ask for data, wait for the reply, then you go on to the next one, so you don't get data coming in from multiple sources. If it was the outstation trying to shout to the centre, you get confusion, and hopefully you detect when you don't get a reply. Usually you put in 1 or 2 retries in there, because you don't want to be, in a sense, swamping operators with alarms just to say that you didn't get a reply that time. And again, there's no direct connection between the slaves, so off-take 1 doesn't talk to off-take 2. They both talk to the centre, and the cycle times are relatively long, because at the end of the day, a lot of the dynamics are the pipeline system dynamics. Pressures across a pipeline don't change extremely rapidly. But I did notice the difference going from a regional distribution system to the national transmission system. Things used to change much more quickly in the regional one because it's smaller, less dense gas. Pressures can change more quickly there. And typically you'll look for a report by exception, so you don't get told everything that's going on, you get told the changes. So if your pressure read 23 bar a minute ago, and it measures 23 bar again, don't alert the operator to that, but alert the operator to changes. So you don't tell the operator this valve is open, this valve is open, this valve is open, this valve is open. You tell him when it changes from open to closed, or open to transit, or closed. So their attention is drawn to the changes that happen on the system, and it's more efficient in terms of data transfer. Say alarms is always an issue, and I suppose there's been many instances of people, 3 Mile Island I think is often quoted as an example of where an event created alarm floods. So alarm management is something you've got to be careful to. Why does that say slave to slave? Yeah, that's probably slave to slave. So yeah, if you want the current data, you've got to ask for it. So if you've got somebody on site and want to get the current reading, you go and inspect. There's a framework that covers these things. I must admit, I tend to not say an awful lot on it because I've never found it desperately helpful. But there's this OSI 7-layer model, so it's a sort of framework for standards which define how different things communicate with each other, and what the idea is that one layer provides information to the next. So the 7 layers, this will go in there. So the bottom layer is the physical layer, so it's very much here's your device and here's the communications protocol it uses. Yeah. So that's sort of your physical, so your cables, your hubs, how you deal with encoding of the detailed data. The data link is then you're packaging up individual readings into sets of readings that come across the data link. You've got network, which is almost like your TCP/IP level, so you've got your IP addresses. Transport layer is how you control host to host and messaging at that sort of higher level. Then sessions, presentations and applications. So you're getting closer, you're going further out to what's almost like the high level operator function. OSI is it open systems something or other, open source interconnection. That's a Googled version of it. Just be aware of its existence. I must admit, I've never found it desperately illuminating. No, it always comes across as a nice philosophical concept, but at the end of the day, somebody's going on a site and they're saying, I've got this pressure transmitter, what's it reading? What messages am I getting in? Can I check those messages? Am I polling correctly? Is it getting displayed correctly on my screen? I'm not going, right now I'm moving from level 4 to level 5 on my OSI model. Yeah. So central monitoring systems. So if you went to a control centre, the so-called man-machine interface. So typically display of data, the favourite is trend plots, which are just time-based plotting. Or you might get a presentation using engineering process diagrams. So there might be full engineering line diagrams with live data on them all, some form of stylised one to avoid overcomplication. Alarm management is important. So report by exception. So it's not the operator's responsibility to go looking for what's wrong. The system will alert you and draw your attention, but you've got to structure your alarms in the right way. So the fact that, let's say, a valve that you've asked to go open is now open is less important than a pressure that shouldn't be high has gone high. You want the pressure one to be brought to your attention. You might want to know about the other one, but you've got to structure your alarms in a particular way. And there are various standards for alarm system design. The MAR8013 is, I think it came out of the chemical industries, but it's been used a lot in this country as a reference point. I mean, people have tried to come up, I think, with more, let's say, more sophisticated alarm handling systems, almost like expert system based. So if I get 23 alarms, what's really the cause, as opposed to the consequence? This was, I think, 3 Mile Island problem, that you start to get alarm floods. Something goes wrong, it causes 3 things to go high, which causes 6 things to happen, which causes 12 things to happen, and the operator gets lost in the morass of alarms and can't spot the root cause. But clever alarm handling systems really don't seem to have made their way much. But there is an extent to it. Most of these sort of central monitoring systems, SCADA systems, do allow you to structure alarms into groups. So you might be interested, well, I want to know, maybe, here's all my compressor alarms, here's all this alarm, here's all that alarm, or these ones are critical alarms, these ones are information only. I might have to acknowledge this alarm in a different way to that alarm. Now, if it's a valve that's got open that I've asked to go open, I can just click on it and dismiss it from the screen, whereas another one I might have to deliberately accept, and it might be linked to a logbook, for example, so you can record that the alarm was received and you took an action on it. They do have the ability to send controls to site, but what they're doing is sending the set point. So they'll say, I can type in 43 flow at compressor X 43, and it will send the 43 out. But the actual control of that compressor and ensuring that the compressor is flowing 43 is done by the site controls, not by the SCADA system. That's too slow. You don't put that in the loop. Anyway, it'll allow you to open or close valves, maybe for special operations, for example, or it might be that you want to divert flow this way rather than that way. For overall operational purposes, optimization, in the sense of overall process optimization, you might be closing, but it's not about safe operation. You're not relying on this system to provide the protection. And I think the phrase these days is enterprise data systems. So data historians have like fast access data systems. And some of them will have add-ons that allow you to do condition monitoring. Business systems might be billing systems or online simulation. So the national transmission system, all the pressures and flows and valves and compressor data is fed into an online system along with future nominations, and is continuously generating a forward prediction of what's going to happen on the network over the next 24 hours. Of course, somebody then changes their nomination and it makes it wrong, but it'll do things like state reconstruction. Some of the data leakage detection systems rely on that sort of thing. So you're starting to connect to bigger, let's say, non-operational systems, so business systems, let's say classically billing, but it might be not nomination notification systems. This is not a national grid site, so just this sort of display. You get different styles, and again, people prefer different colours, and every time a new system comes in, people will look, what's the best way of presenting data to the operator. But that single loop flow controller, the most recent control system that's been put in to the Gas National Control Centre, they made the interface on the SCADA system looked very much like that flow controller. Previously had all sorts of data shoveled in boxes, and as sites change, you were finding you were getting pipes running over your data boxes, and your displays become, if you're not careful, confusing. You need to be simple to the operator. But you can see like green, yeah, they're okay. That pump is displayed in red, so red, green. Colour blindness is always a bit of fun, because you'll get operators who are colour blind, and sometimes the background you've got to be careful of. So there's presumably an alarm on that pump at the moment.
Is it not a restricted occupation for colour blindness?
Well, I think it's not restricted. I think, red, green, because there's usually also displays of status indication. One thing they did at one point is they had sort of quite a light green background, and like particularly green read. This isn't too bad. They put them in a box, and that stands out. But if you had a slightly greenish coloured background with a green reading on, it doesn't always stand out. It's not contrasty enough. Again, there's been a lot of studies of ergonomics being done, I think possibly some at this university, and trying to take account of all sorts of things. And they look at there's been experience of pilots across the world who've got confused by their instrumentation and flown into mountains because they thought they were 10,000 feet higher than they were. Now they were misreading a digit. People's perception of data is quite difficult. But typically each site will have its own. So the package will come with a set of tools that will allow you to build these diagrams and perhaps have a set of standard symbols, like pump symbols, but then you'll link them to the data and provide operator data displays, or you get trend plots like this. Just to make that looks like a particularly horrible trend plot. What I tend to find is then you get people downloading data onto spreadsheets, which can be useful if you're trying to share them legitimately share some data with a third party. So if I would get involved in discussions with, say, an upstream operator. This is what we saw on a gas quality reading on this day. If I could just get that data onto a spreadsheet, I could mail it, and I found that I was able to provide them with data, and they were usually providing me with JPEGs. So a screenshot like that, but if you want to look at it a bit differently or try to match data up, well, a JPEG's no use to you. So being able to get data off systems and perhaps share with operational counterparties or your maintenance department. So again, the typical use might be was it incident management again this morning or something like that. So if they've discovered corrosion on a pipeline, typically one of the things the control room would be asked was, what's the highest pressure you've seen in the last year? And you want a system that will allow that question to be answered very quickly, so they can put in place the right operational restrictions. So data historians are very good at that, because what they do is they allow you to grab a lot of data very quickly. Okay. We started using data historians on the gas side, but we're still only filling data in once a minute. Our electricity colleagues are obviously more interested in 50 hertz, so they generate a hell of a lot more data than we do. Because it's fast stuff. But you do get asked those questions. They're in operational timescales. You can't go, well, I'll go and get the tapes out and we'll send it to the IT department, we'll come back next week. They need an answer there and then. Otherwise they'll say, well, the restriction is this, and it's considerably lower probably than operationally you'd be comfortable with. Right. And that brings an end to my proceedings and brings an end to your lecture course. Although I believe you have assignments now.
We are dealing with that in terms of these are volumes of data. How do you deal with the backup systems for purposes of?
So what you'll find is there's a lot of redundancy in there. So at one time it would typically have the online system, a hot system, so it's getting all the data in the same real time, and maybe a cold standby system. So you've got 3 levels. Quite often it's 4 levels now. So you've got maybe 2 and 2 working together, and that's again another thing that a data historian can give you access to, because that's another way of holding the data, and you could port the data back into your SCADA system if you needed it. But yeah, and they tend to state higher and higher standards on things like disk integrity, but you're usually kicking the data into 2 places at the same time. So if you lose one thing now, where you will lose out though is if you lose your data link to the site, you typically don't get a catch up from the site. Now, so if I scan the site at 25 to 5, then lose communication, then get it back at 4:45, from my central monitoring system point of view, typically I won't know what's happened between 25 to 5 and quarter to 5. I won't get any data that's occurred in between.
No replication system.
There's not. However, for like fiscal measurement data, that is held on site and dumped across on a daily basis. So you can always go and do that. But if my pressure was okay at 25 to and quarter to, it's usually been okay in between. And bear in mind, I'm relying on the site to make sure that it operates safely. So it's not performing a safety function. That's one of the very reasons why you don't put these sort of things in the safety loop, because if the data link goes down, what happens if something's gone wrong in between? I know. I think filters were a bit of a worry on that at times, because if you have a problem where a filter bursts, you can monitor filter DP and have an alarm that says the differential pressure across the filter as it starts to get blocked is going up. But if it bursts in between scans, you miss out. So then they tend to put so-called latching filters in. So in other words, if it went high, it would latch it in, and then whenever you next ask for the data, even if it was an hour later, you'd still get that alarm, because you could get a very quick event on there that would be happening in between scans. So it depends on what you need the data for. Say a lot of fiscal data is held on site, but the majority of pressure data is, it makes a measurement, and then if it's polled, fine. Otherwise, it waits and it makes another measurement. But the central system will have a lot of redundancy on it, as I'm saying, and usually across more than one centre, and lots of hot replication. But you've got to look at the performance issues. That if one of your systems has been down for a while, how long does it take to catch up? Because you are often bringing a lot of data back in. So if you've got your main system and your standby system, they're in sync. Say your main system goes down, so your standby system's got all the data in, so you can start working on that. But when you bring this one back up, what you want, that's not only got to start doing the new stuff, it's got to do the catch up on the old one. So you've got to make sure you specify your system, look at the metrics on how quickly it can bring itself back up because you might have to do it, because you might just generally be software changes. Our friends at Microsoft often will issue software patches, which mean taking things down as well. Another reason for having redundancy at that central level. And usually there's like the data links, the telemetry links are typically duplicated. So I mentioned satellite, but typically you'll have maybe satellite and say an ISDN line. So if you can't get it on that, you get it on that. So you try and minimise the chances. But if the telemetry unit on site breaks, then you've got to send somebody out to investigate, and you've probably lost that data in the meantime. But on a lot of systems, you'll have other stations nearby, so you'll know if pressures are going wrong. Unless you're on a single feed sole supply, and the UK system is quite integrated and looped. Might be a bit different on a transit pipeline system, where you're going point to point to point to point to point, so and maybe they're quite a distance apart. But even so, that's where online simulation might come in. You know, if you've got a state estimator, you can fill in missing pressures on the system, or it'll tell you that, hang on, the measured pressure and the inferred pressure, there's an inconsistency here. And that's where leak detection might be a tool. You can usually buy leak detection systems bulk as like add-ons. Again, it depends on the complexity of the system and how good have you got enough data in the right places.
Maybe what do we take out from this lecture for the exam project? It's a bit, of course, it's a big area.
Yeah. And of course, well, you might think, well, some of it is quite descriptive, so how would you set an exam question on something that's descriptive? But there's some bits that maybe had, let's say, example numbers in, so maybe that would be easier to set a question for. Maybe you might think that way.
Are the control systems, are they still quite, are they run on private networks still to try and avoid third-party interference?
Well, there's an awful lot of cyber security now is a big issue, and you've also got to be the control centre. It's very segregated, lots and lots of firewalls, and if you ever want to bring anything in, but you've also got to be quite careful about when you're connecting sites. At one point we had a party wanting to connect to power. They were connecting a power station. It was doing the meterings, and they have to give us the meter data. And they said, oh, well, what we'll do is we'll pass it through our corporate cloud system. You realise, if you're not careful, what that means is we can go onto our telemetry station and get into your corporate network. I don't think you want to do that. There's lots and lots of firewalls. Yeah, it is deemed like a key piece of national infrastructure and is subject to all the oversight that implies. Oops. And when people, one of the issues with things like flow computers and some of the telemetry outstations now, they're more complex. They're almost like little computers on site, so therefore people go and connect laptops to them. So what do you do about virus management? You've got to be you do have to be very controlled about what you allow people to connect to it. It's segregated from the rest of the corporate network, and but as a non-control room operator, I often wanted to look at the data. Now, I had a read-only version of SCADA, but one advantage with something like a data historian is, again, it's another level of separation away from the SCADA system. It means if I'm doing what I used to do, where I was looking at a lot of data at the time, I'm not slowing down the control room's operations, I'm looking at a different system.
For the exam from this segment, how many questions?
Oh, I would never set more than one. Right. I brought some light reading. So if you really want to get into no, you don't want to start looking at these. They're fine. Well, this is the point. You see, control systems is big. There's lots and lots of them, and this is more control theory. Rather, the trouble is a lot. Let's say control as tools sometimes doesn't get too close to practical application. Yeah. There are a lot of mathematicians working in the control systems area, and they love nothing more than to have n-dimensional matrices and things and talk about things in unit hyperspace. But I suspect, but facing with a bit of plant, they might struggle. This is trying to stick to slightly more the what I might call the engineering end of things. That's why I didn't major too hard on the OSI model. It's a nice conceptual thing, but well, you do what you see fit.
From a regulator perspective, as a regulator, if an operator is coming up with a system, most especially as a regulator, what would you look out in terms of which other system or monitoring system?
I mean, I suppose there's a relatively small number of big SCADA manufacturers out there, all with well-established records, and typically, I think we've got an exposure when I was working at National Grid, speak to other people who usually do some visits, for example, and you get that. So if somebody is confident and happy with the way the system works, and you can also see the way that they've implemented things like pictures. Pictures are very important for the operators. The operators will obsess about site pictures more than almost anything else to start with, because it's what they can see, it's what they're having to deal with on a day-to-day basis. Dear Ask, I should be able to clean this up. But no.
Matthew, he has one doubt in Arabic. Clearly, Arabic.
Do you have
Like
is there a phrase in Arabic? Something like Ojalá. 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 A phrase like that means like so once.
It could take a long time.
Like
Maybe inshallah.
Ojalá.
Maybe inshallah.
He's telling please.
No, it like it's like the equivalent to English would be like hopefully.
Oh, inshallah.
Inshallah.
Well, I think it's it looks like it's going to run out. I've got a feeling I'm going to be waiting for a while.
Hopefully, yeah.
If you work and dry, don't just use a small wet section.
I mean, we use it in Spanish.
We soak one section because when
Get some other wipes.
yeah, but it's a permanent.
Yeah, I mean, what we would find is probably that our regulator, the health and safety executive, won't say you should use this and you shouldn't use that. It's up to us to demonstrate what we're using is safe, and if something goes wrong. But if you're like the EMUA standard is not, let's say, an official standard, but I think it's accepted as representing something of best practice. And we did have the HSE coming in and looking at things like man-machine interface and human factors things, because human factors in control rooms can, well, inevitably make mistakes, because also you've got a lot going on and it's the middle of the night and you're tired.
Yeah,
True.
You misinterpret an alarm, or you miss an alarm.
And they hear
Yeah. So the human factors bit does play a big part.
That's so true.
Roll the ball around and blame it on someone else.
Yeah. Well, I'm going to make it sufficiently. I'd worry less about that one because it just looks like a wobbly line, whereas something that's got pictures of valves and 2.1 bar is a bit more of a giveaway.
I expect these whiteboards are pretty nagging anyway. They've got a matte surface now.
And do regulators tap into these systems at times? Can you remotely be able to access them? Or?
No, in a sense that's what you don't want people to be able to get into your systems.
No, I mean for visualization.
But, well,
Maybe
in
not.
some cases you can provide visualizations outside. Well, again, you might use things that the data historians can be used to generate different visualizations. It might be that maintenance staff want different things.
consider it, or two.
Yeah, just 30
I think
seconds.
It's okay.
might get some toilet paper and then I can wipe off the excess liquid.
Almost there.
I've been wondering why the bottle of cleaners empty.
Yeah.
One disadvantage with this course is I don't know before I come here who I'm talking to or what your backgrounds are, so in a sense I can't slightly tailor the examples.
Okay. Yeah,
So
yeah.
you come along and might find that somebody knows an awful lot about one thing.
Mechanical,
Yeah, good mix.
Yeah.
There's
Yeah.
a few people that work.
mechanical, chemical.
Yeah.
One of the lads is
Yeah.
he's working for a company at the minute.
Mechanical,
Yeah,
chemical,
I've basically more been into
Yeah.
upstream, a
Yeah.
little bit of drilling. And,
Yeah.
Yeah.
Yeah, I spent a little, well, when they were commissioning the rough storage projects, the time I've worked offshore. It's the one time I managed to work 26 hours in one day.
Wow.
Well, actually, it was 37 consecutive hours from leaving home to getting home.
26 hours.
But the question was, so
Some
one day
facility.
finished and the next day started.
Oh my God.
Something down every time sheet. And if you had it up to my normal hours of working technically, I'd
Is that what?
26 hours.
Are you not tired?
Or commissioning, I suppose.
I'm tired.
Basically, fabricator to turn an academic, I suppose.
Yeah.
Oh, finally.
Final
I'm going home.
Sure.
Yeah.
Yeah.
But it was like that.
Oh my God.
That's the reality.
That was the final switch, yeah. Like
You can use a bit of that cleaner.
7 days.
The paint. So
maybe live video.
That was
I'm going home.
It doesn't need to send you.
No. I'm going
You
home.
know, live video, home live video.
Is it green proof?
Yeah.
Of course.
Well, that's
that made all your pictures pink.
It's okay if I take outside, yeah?
So how do you
No, there is a place.
So do you all know what assignment is it an assignment or a project that you've got to do now?
Yeah, an assignment.
Assignments. Yeah.
I
And then
guess it's a
also
project
projects
or-
as well.
The project, this national grid
How about
carried
jeans?
out the project
Just
converting natural gas
Kevlar, not
pipeline
with
to
the
a CO2 line.
Oh yes. Yeah, that was well.
the quite thick.
You remember the
Most of
project?
it's
right?
What's her name? She used to coordinate this course about 3 years ago. Race, Julia Race, was it?
James.
Yeah, but yes, I went to one or two of the talks because at the time I had some knowledge in gas quality measurements. I went in the early days. I went into some of those. So one of the issues with CO2 pipelines is if you get a break, CO2 being denser than air, will fall down into dips, whereas natural gas it disperses upwards.
Yeah, but I mean, they're not wind.
And
I've got 3 pairs. I've got those of
So-
pair like which are waterproof.
so you're having to monitor carbon dioxide and the escapes
Today
and
these are good.
so on.
You get
And
quite a lot
I
of.
think some of the
you get
chemistry we were going to use was
with the window ones. It's so
quite
thick.
complicated
You're
as
not
well.
writing like that, yeah, I don't.
As well as, I suppose there were, I think, the likes of the people here and perhaps your project maybe focused on, was all about the different, there's different stress mechanics are different. Because we were looking at, I think, one of the original Scottish feeders. But I think, unfortunately, those sort of carbon capture and storage schemes haven't really got off the ground in a big way.
Thank you.
Thank you.
Okay.
You've never been there after that.
Right.
Thank you.
Right, okay.
I feel like I learned a lot today.
Yes. Well, if you had, imagine if you had a few hours of instant